All right, so these are mostly straightforward product rules, but with a few complications. So 2.1, you've got a grading system that uses first initial and last initial. And so how many different possible pairs of initials are there? So that's a straight product rule, 26 times 26. The subtlety here is that it asks what's the smallest class size that forces you to use a different system. So it's slightly different from what's the maximum number of unique initials. It's actually how many students can you have that will force you to use a new system. So it's actually the number of pairs of initials plus one, right? So whatever that turns out to be, 677. And that's actually a subtle application of Pigeonhole Principle, although you don't have to spell it out in this case. But basically, if you have 26 times 26 students, so think of those as objects being placed into 26 times 26 boxes, which are labeled with all the possible initials, the ceiling of that is exactly 1. So Pigeonhole Principle tells you that worst case, one object will go in each box, right? Or best case, one object will go in each box. If you add 1, this becomes 26 squared plus 1 over 26. That's the ceiling of 1 point something. That brings you up to 2. So now Pigeonhole tells you at least one box has 2 people in it. 2 students must have the same initials at least. So that forces you to come up with a new system. And again, it could be that you have 2 students, total collected class is just 2 students and they happen to have the same initial, and your system will break. But it says what's the smallest class size that will definitely force you to come up with a new system. So how many students can you have, even if you're very, very lucky, that will still force you to come up, so you got to add that 1. 3 is straightforward, multiply your number of ways to do each task. So choose size, that's 4 ways, choose a color, that's 6 ways, choose an emblem, that's 3 ways, and I don't think anybody got tripped up on the fact that no emblem can be considered an emblem, right? So basically 3 choices for what you want on the pocket. So that's just the product of those. Automobile dealer, same thing, except that I think you're also supposed to multiply by 3 because you have 3 different packages, but the wording of that's a little confusing to me. But I took it to mean 3 packages, 2 styles of seats, 3 colors, 4 different radios, and 5 exteriors. But for some reason you have to choose a package along with all of those options.
Doesn't the package refer to the style of seat, the choice of radio, and the exterior?
It's possible, but it says several different options for each of 3 different packages. So I took it to mean like package 1, you pay with cash and we discount you $100. Package 2, you do a 10-year finance or something like that. I don't sell cars, so I don't know what they had in mind. But I would try to be less ambiguous if I wrote a question like this. And if you saw a question like this, you can ask. But anyway, product rule, I think everybody got that. So question 8 has a subtlety in it that I missed the first time through. So you need to choose which courses to take. So you're choosing 2 of 4 lab science courses. When you choose 2 courses, presumably the order in which you choose those courses doesn't matter, right? So it's not a straight product rule if you can choose your first course 4 ways and you can choose your second course 3 ways. That looks like you have 12 ways to choose your science course, but in fact, if you choose course A and B, that's exactly the same as choosing course B and A, right? So you need to actually do something where you divide by the number of ways that you could pick those 2 courses. So this actually turns out to be 6 possibilities for your lab science course. Literature course, you have 2 courses, you have to take 1, so there's 2 ways to do that. So it's 6 times 2. 2 of 3 math courses, well, you could review that. Again, if we cared about order, it would be 3 times 2 is 6 possibilities. But if we don't care about order, think about it like this. You're choosing 1 of 3 math courses not to take. And the number of ways you can do that is exactly 3. Okay, that's the same as choosing 2 math courses, 3 ways to choose the first, 2 ways to choose the second, but that 6 ways is treating, course A and B as being different from course B and A. So you have to divide out by the number of arrangements. And then 1 of 7 PE courses is just 7 possibilities. So that one's a little subtler, and I'm not sure in section 2.1 we talked about that, so I don't know what that's doing in here. Number of integers from 100 to 999 that don't include sevens, and this one works best if you just think of it as a procedure of picking a legal number, right? So this can be anything from 1 through 9, but not 7. Because our number has to start from 100, this can be anything of 0 through 9, not 7, and this can be 0 through 9, not 7. So you can do this 9 ways, you can do this 9 ways, you can only fill in your first digit 8 ways. So your total number of possibilities is 8 times 9 times 9. And then the last one, 10-question true-false exam, but you're also allowed not to answer, so you actually have 3 possibilities for each question. And you've got 10 questions, so product rule is just 3 times 3, 10 times. So that's 3 to the 10th. Most people got that. So in 2.2, we've got another number question. You're forming 3-digit numbers. You're allowed to use 1, 2, and 3, but you're not allowed to repeat any digits. And then they want you to actually list the numbers. And then in part B, 2-digit numbers with no repetition allowed, and then 2-digit numbers with repetition. And then question 6, 3-digit numbers formed from these 5 with some other qualifications on those. So go ahead and work through those, and then let's get started on question 6, and then we'll talk about question 6. But go ahead and work on the 2.2 questions. Some of you already started those. And work on 2.3. There's a way to zoom this, but I don't know how. Yeah.
I accidentally kicked one of our markers underneath the door.
Oh, I can go rescue it.
Good marker. Yeah.
No repetition.
I read repetition as you can have the same, like you could have, say, 3, 3, 3.
For the repetition,
Mm-hmm.
is it as you
No,
can
okay, I
have
think I know what it is.
something like that? Or you can have something like that? Or would that also be considered a repetition?
I think that's a repetition also.
Okay.
So I think
3 1 3
each
would be a
digit has to be
repetition.
unique.
Thank you.
Yeah.
And it says to write out the numbers.
No repetition. 2 digits, no repetition.
If you're your one digit has a chance of being
Couldn't technically all students only took one course, so there's no overlap? Are we doing, what question are we doing?
For 6A, I got 0. I have 18 and 12 and 30.
Yeah.
18 plus 12 is 0. And 6B, if 5 aren't taking the class, you have a total of 25 with 18 and 12. So you have 18 plus 12 minus 7 is 20. And that's 30. And so 5 people must have taken
And then 64. Alright.
The overlap is people who took both courses, so the 5 people they didn't take either, so wouldn't it be like out here?
So,
Yes, it would be. I'm choosing to ignore it. So 5, 18 plus 12 minus 5 is equal to the total number of students. Because when it's 18, so it's equals 5, and there's only 25 of them. So 5 of them must have taken the same class.
alright, let's straighten it out.
1, 2, 1, 3.
Is asking you
Try to find how many took both.
So where's your answer for 2-2? Oh, there it is, 2A, 2B. Okay.
For B,
Which
yeah,
one?
for sorry, 2.2B, order repetition. 1 and 3 and 3 and 1 are going to be 2 different permutations, right?
Correct.
Okay.
Isn't it 2 times 2 times 1? I mean, the plus part's better. I think we're using plus.
What was 2A?
Bruce will get you the same answer.
Yeah, I guess the same
It
answer, which
still
is
does,
funny.
but-
But yeah, technically that's a product rule. So 3 ways to pick the first digit, 2 ways for the second, 1 for the third. Okay, yeah, I like 2.2.
Yeah. 2.4.
So how did you get 6?
Can you get with 1?
So 6A, we have 5 choices and then 4 choices, and then we only have 2 choices.
You're not allowed repetition.
Yeah, we're not allowed. So we can't use the even numbers
So
before.
would that be, we need to use the even number then, so when the first one be like 3.
We would have 3 choices. Wait, no, we'd
3
have,
times 1.
wouldn't it be 4 and 2?
Well, we have 5 numbers to choose from. 2 of them are even, so we can rule out. So there's only 3 numbers left. So we get 3 numbers to choose from.
Number 2, or are you starting with
Yeah, but we don't have to rule out both of the even. We only need to rule out one as the even.
4
Would it be 4 times 2?
2 would be 2.
Would it be 4 times 2 then?
For the second digit?
I think that's
One, two,
Part B is after, part A that is how many.
we need at least 4 of these. So let's,
now this number makes sense.
and then now there's 3 numbers left. This one's reserved for the last one. This thing is reserved for the last one. So for this next one, we can choose this one, this one, this one.
I think it'd be 4 times 3. That seems reasonable.
And there's only 1 number left. This last one.
Yeah, well, 8 possibilities. That's not
I think 6 is right.
this has to be at least 2. For each of those, yeah. Okay.
So 4 times 3 times 1. How did you get those?
We have 5 numbers, and we know that the last one has to be even, so we can basically, we know we can use one of these even numbers. We just have to have one even number left in there. We said we have 4 numbers to choose from for the first one. Then we have 3 numbers to choose from the second one because we can't use the other even.
Okay,
And then we know we have to use an even number on the last one.
but you said there were 2 even numbers you could use for the last one, right?
Because we could or could not use every number on the first one. In which case we would put 2 here.
Yeah. So I think that's the right answer.
But if we end up picking an even number on the first one,
Well, pick your last digit first. All right, you've definitely got 2 ways to do that. It's got to be a 2 or a 4. And then that leaves you 4 possibilities for your first digit. And now you've picked 2 digits, and since every digit has to be unique, there's only 3 options for the middle digit.
Can't be 2 or 5 other options. So there are.
Yeah, so I think that's right. How many?
It's a bit more complicated than that. Like, it needs cases.
Yeah, you need cases for B. Not too many.
This is all. So the first digit can be 2. The second digit could be 2 or greater than 5, but 5 is our greatest digit.
Wait, isn't it? It can't be 1, 2, and it can't be 5. Wait, no, it can be 5. Wait.
wouldn't it be 3 times 2? That's all.
I need to like write a case.
Yes, it's okay. Don't know. Kind of. There's a bit of an issue because
The first order has to be 2 or greater.
then there are no options. This way
So 2.
This is what numbers because you could put in a 1.
1, 2, 3, 4 times 6.
I mean, Republican Party is
And then 5. Greater than 5.
let's say any number but the first time, so we have 5 options. I don't have the side equation.
5.
I think it would be
Then this would be
plus 1 and a half.
Economy is better than
2 or not this number. Yes, because both of them and yes, but you know about
So if the first is 2, we know that it has to be 2, and we know that the second has to be 5. And then there are 3 choices left. And then if the first is 3, 4, or 5, then we have 3 choices for the first digit. That's 1 times 3. Because if the first is a 2, you have to have a 5 after it. 3 choices. And then you select one, any digit can be after it. It's 5 minus 4, and 5 minus 2.
just don't raise the
I don't like that. Most people don't like it. I don't think anybody thinks it's but they're already taxed at a certain amount. They account for the majority of the change. The lower class is not going to
well, the middle class tax counts for everything.
The rich,
Top 1%, they count. Yes, but there's very.
Yes, but they're revenue compared, so they get
B's
taxed.
are not sixes.
That
That looks more like a 6 on a B.
It's like giant.
It looks like 6
See, look, the important thing to look at is the stem, not the helper.
That I can straight.
If the top
He has a straight spine.
is the third
Great, I did it like that.
It still looks like
The only thing upside down 9.
That doesn't work because.
No, it doesn't. Because you start out by filling in this, they have the same there. Once you have the thing.
There's no reason to believe what you're buying.
Yeah, but now I can tell they're beans.
So, is this a B?
No, that looks like the notebook this thing.
It's just like a stick with
It's
a
too long.
Is this a B?
The proportion won't right.
Okay. Is this a B?
Yeah, you can write your grades like that, but that looks terrible. It's hard to write like that. It's better to do one continuous stroke. To write
He has the right to take your money.
Okay, so 2.4.
Because he does take our
He does not take your money.
0.4.
You pay him for goods, that's not taking your money.
Relax. Sure, yes, but you also pay, so, under that same theory, you pay the US government in terms of taxes for protecting and keeping your state, maintaining the roads and stuff. Right?
Currently, we pay for a lot more than that.
So you take Jeff Bezos, my boy, he uses the roads a lot more than anyone else because his company uses the roads a lot more. Therefore, he should be paying for all of it.
Pays for every car that's on those roads. Oh, you didn't hear it? That's what the money that goes for. Along with tax, but tax, that's the entire point. You will, are using the road with a different kind of, like a big vehicle that pays for tax because it's costing you.
These are my answers.
Yes, and then what I'm saying is that's the example, and that is an example in action of Jeff Bezos.
That's a 4.
Why would the same thing apply to Bill Gates?
What's he doing?
Pick anything except for.
What is he doing that making the government need to?
So the government invests heavily.
Like 7.
6.
Yeah.
Yeah, that's
He
what I
hasn't
said.
given that back.
And then 2B, how many bit patterns have at least 2 ones?
He's given people.
So you take all the bit patterns that don't have at least 2 ones, which is 4. So the total amount minus that.
Yeah, but.
Yeah.
But
So they invented it. They don't benefit directly.
Yeah, but they benefit because they got what they wanted when they paid it. Sorry. Because
Actually, I guess it'd be
if
3.
there are 30 total people, 12 into this one, 8 into this one, there is no room for more. That's what you're trying to find.
Would it be
You know, it's
3?
zero because if 12 took this
I
one,
think there's
8
only
took
3
this one, there is
possible
no room for-
things that don't have at least 2.
What did you get for 2-2?
2.
Actually, wait, no.
3 parts.
This one?
6, what about part B? Part C.
Our organization would give it 10.
But it can also be like subtracted 1 and 4 or 3 and 2. There is no overlap. I do think there are going to be, well, the overlap I think is going to be.
We did a problem on this.
30, you know.
Oh, 2, 2, 3. Well, 8 stuff at the top. Wait, no, that's 4. I think I understood.
Wait, not Can the 8-bit string start with 1? The principle of inclusion exclusion?
We did one that's a bit different.
Do we want to separate those?
We did how many 8-bit strings start with a 1 and end with a 0.
Oh, okay. Oh, okay, yeah, we just missed.
I'm thinking like, it seems like a permutations problem.
Yeah.
Actually, wait, no, it can't be permutation. Permutations assumes every digit is unique.
So,
2
P
combination.
was the 9. P were the options for B, these were the options for A.
Okay, 6, 6, 9.
Yeah.
Okay, cool. What about question 6?
6 and 2, 2.
But it's less of this is.
So three different numbers. Oh, okay.
Oh, you're making that little one.
So then 6 for even numbers is 5 times 4 times this, because it has to be 5 digits. It has to be
Okay, last digit has to be.
Order doesn't matter, only 3.
Okay, so that's a 2.
And that's just, and then you got 5 for your first digit, you got 5 options. Oh, you have 3. One you have to save,
3 times 6.
save. And then that one, I went about it probably a little weird.
Like, they can be in any position.
And then I did everything.
That's the
Yeah, so they're equal to 2.
Yes.
So yeah.
I feel like
So we're looking for
24 as well.
for A, yes.
Without writing them all out. Yeah, I'm not sure how to find it.
I mean, it's not a small.
I don't want to write out the 255.
This is just.
It's on the blank, or you just call it 1.
So when I know. So are you registered? That's okay, I get it. Now, thank you. I think you said the exact same thing. You did. I did. Another person was like No, it makes sense now, like, as I.
I don't follow what you're saying at all.
I'm just thinking out loud. Don't.
Government vote so and Jeff Bezos uses that. And we need to add.
Could this be like, this would be stupid. Could it be this?
But
Billionaire.
well,
I keep thinking that's like a weird word.
is that the government aid
Times
and the
7
government
times 6.
aid, the government.
Because you have 8 places to put a 1, and then 7 places to put a 1, and then 6 places to put a 1.
That's what I was trying to derive, because I was going in a really fast way. I don't know why.
Without the government itself. Not you. We don't know the government.
336?
That sounds reasonable.
Sure, but that's like the 1% of the 1%.
All right, so let's talk about these, and then let's go on to the Venn diagram, inclusion, exclusion.
Most people don't murder people, so they shouldn't be allowed to say you can't murder people. Because so few people do it. I mean.
So first of all, the number of digits questions. So how many 3-digit numbers can be formed from 1, 2, and 3? Most people got these, right? So if no repetition of digits is allowed, so you've only got 3 digits, you can choose your first digit 3 ways, you can choose your second digit 2 ways, and your third digit 1 way, so there's 6 possibilities. And I think everybody listed those out. 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. And then for B, no repetition of digits allowed. 2-digit numbers, so 3 options for the first, 2 options for the second. So that's still 6. And then for C, 2-digit numbers with repetition allowed. So that's just 3 times 3. So that's just 9. So not a big surprise there. So question 6 gets more interesting. So 3-digit numbers formed from the numbers 1 through 5 with no repetition. So that's a straightforward 5 times 4 times 3, right? Number of ways to choose first digit, second digit, third digit. So if your number has to be even, the easier way to think of this is to fill in this digit first, because we know that's got to be an even number. So this can be either a 2 or a 4. So you've got 2 possible ways of filling in that digit. And then once you've chosen this digit, now this middle digit can be anything except what you chose for that last one. So there's 4 ways to choose that. Now you've picked 2 digits, so you have 3 choices left for this. So that brings you back to 24.
24?
24. So 3 times 4 times 2. And then if you want numbers greater than 250, this breaks down into cases. So 3 digits from 1 through 5. So there are a few numbers in the 250-ish range that'll satisfy this requirement. So your first digit could be a 2 and a 5. How many ways can you fill in this last digit? There's 3 options. It could be a 1, a 2, or a 3. Sorry, a 1, a 3, or a 4. So if your number is, can we do Amazon debates outside? Okay, thanks. If we do 250 something, there's 3 ways that you can write a number like that. And if we want a number that's larger than the 250 range, right, this could be a 3, a 4, or a 5. So you've got 3 ways to fill in that digit. And then the usual argument, once we pick that digit, we have 4 ways to pick this one. And we pick 2 digits, we have 3 ways to pick this one. So this is 36 possibilities, this is 3 possibilities, and we can find this number, complete the procedure of choosing a number, either this way or that way. So now it's a sum rule, 36 plus 3 gets you to 39. So that's a combination products and sum. And there are other ways to do these, and I saw at least 3 different approaches to this even number question. You can try to find how many odd numbers there are and then subtract that from the list of all possibilities, and so on. So let's look at the inclusion exclusion. So 30 students surveyed, 18 of them took calculus and 12 took C++. So we have this rule from set theory. Right, so the number of elements in a union is equal to the number of elements in each set minus the number of elements in the overlap. Right, so you subtract anything that would be counted twice. So 30 students. So let A be the set of students taking calculus. B equals a set of students taking C++. And so cardinality of A is 18, cardinality of B is 12. And we know every student took at least one course, so every student is contained in either A or B or possibly both. So we want to know how many students took both calculus and C++. In other words, we want to find the cardinality of this intersection. Well, we have a group of 30 students, so if we take, let's see. So if you take all these students and you take their union, right, unions don't include duplicates, it just gives you a set of all the students that took at least one of these courses. So since the group of students is 30, that tells us that the cardinality of A union B is equal to 30. Okay, that's sort of the critical detail. And now you can just plug these into here, and this rule tells you 30 equals 18 plus 12 minus the cardinality of the intersection. And so that tells you the intersection is empty. So no students took both calculus and C++ in that case. Now, if 5 students did not take either of the 2 courses, that tells you, so that's A. If 5 students did not take either course, that tells you that of the 30 students, 25 took either A or B, right? Took either calculus or C++. So the cardinality of this union is 25. And that's got to be equal to 18 plus 12 minus the size of the intersection. And so that tells you, if you just do the algebra, that the intersection must contain 5 students. So 5 students took both. And that's how most of these inclusion, exclusion questions break out. So if you want to do a Venn diagram, let's see what the Venn diagrams look like. Yeah. Yeah, you got the idea. So here's calculus. Here's C++. Here's the students that are in both. Here's the set of all students, wavy lines. So if this set contains 18 and this set contains 12 and the collection of the sets contains 30, there can't be any overlap, right? If there was an overlap, then the collection of students in both of these would end up being smaller than 30. So here's the case where there's an overlap in part A, they're disjoint. All right, so the number of things in the union is just the number of things in each set. And the more they overlap, the smaller the number of things in the union. The extreme case might be something like this. Here's a set A. Here's the exact same set that we call B. So the number of things in the union of A and B is precisely the number of things in A, which is precisely the number of things in B, right? Because they're exactly the same set. So the cardinality of A union B would be right, basically twice the cardinality of A minus the cardinality of A or B. That makes sense? All right, so we've got 15 minutes. Go ahead and do the last question, 2.4, number 2. Single character stored in the computer using 8 bits. How many have exactly 3 ones? How many have at least 2 ones? So this is just a good old combinational problem.
We got 2
Okay.
It doesn't seem like it's
But it doesn't give an order or how many have exactly has exactly 3 ones. Has exactly 3 ones. How many bit patterns have exactly 3?
From the original footage here.
so if you do
That gives us every combination.
25, we're like, I'd say, if it's calculus or maybe I just do like 5 of them say I didn't take it.
So that would give us 3 ones, and then the rest of them.
He also
would be
lies
3
about
ones. Or 2 of ones. But we
Okay,
want
okay.
something that's
So,
exactly 5 zeros, and exactly 3 ones.
It's a real thing. They're not trying to they're so far in this thing. And then they're
okay, get rid of the 5 we didn't take either course. So we got 25 students, 18 of us that took it out.
It was sure, okay. Well, we got 25 students.
All of them.
For the first case, you can pick 2 digits for all of them.
Overlap. If it was like
He
this,
was doing it with the
Then
intersection.
for the second one,
here,
see something wrong.
so if there's exactly 1 student in both,
It won't work like
that
that.
would mean 17
I
students.
only expect that. From what I've seen so far,
Yeah. Basically. So
Yeah, so it's kind of like what we did I remember it was like
what
either
had
do
two
something
sessions
or
at
actively.
least that would be.
Well, I got for example, but we didn't do it.
I'm like,
The problem was how many digits we're gonna start with.
It was before.
Yeah,
So when you try
and the Great Recession actually fell worse than the Great Depression. I know that. No, he didn't feel it. There's a reason for that.
yeah, right? It's like,
so
oh man.
it takes some but
Is that what we did? No, in fact,
Yeah, it took a little bit to get it, and as soon as it did, the economy was starting to get better. It was doing better, it wasn't doing the steepness of whatever they're calling it, how quickly it's better. Yeah, sorry.
It'll be quicker to do it that way than the
The
school.
slope isn't high enough. For you actually, like, you have.
So,
Because if you put, it's like the whole thing, the economies are falling. Therefore, you have to have 3 ones, 3 ones, and 5 zeros. So I'm not giving them all the directly increase the economy. I'm saying that it's bad. First one, second one, third one. Well, a bubble is a bad thing.
I guess it's sort of telling it that.
A bubble's about
Zero.
Well, no, how would you keep a bubble from popping? How about that? Don't make it so fun.
12 by 12.
No, bubbles aren't
I
bad.
don't know if
Because
I
we're.
think Polly, I'm not 100% sure if it's right, it's probably wrong, but
Okay,
I was trying to think, splitting is actually basically 2 4-digit numbers. There's 4 possible ways to do 3 ones in the center, 4 possible ways to do 3 ones in the side. Then, if you were to do the whole thing, you could have 1 1 on the side and 1 1 2 2 on the side, 1 on the side.
If I do 4, but it calculates all of the possible ways, I get 10. So if I do 8 and then list all the possible ways, it's going to be a lot more than 1 end.
No, not a housing position. Because I'm not so many rules.
Yeah, that's what we're coming go.
There's always so that it's not big rate refresh. Or a big rate refresh.
Some kind of combination between
Well, that's what we know to see.
Here's the thing, 8 times 7 times 6 is way bigger than 2 to the 8.
I feel like no matter what we do, whoever becomes president.
This is going to be a side one. We're going to go through it.
It doesn't matter if she's going to be
On Monday, we're going to be writing out all possible combinations.
Honestly, we probably would have figured it out by now if we just did that from the beginning.
Okay, let's go.
But I'm tired of all the just accusing of something just to accuse it. People coming out with something just to accuse it.
You'll be here till
I'm
Monday.
full straightforward. You can't give it time.
We'll come back on this and he'll still be trying to find it.
If you can't stop it.
You're pressing the right habit. I would.
There was an interview where she straight said that she didn't want
1 or 0.
And then.
Everyone has some
So first, we want to figure out
brute force.
Oh, cool. Brute force these all the time. So different way to think about this. Think about what position you're going to put your first one in, and then what position you're going to put your second one in, and what position you'll put your third one. Okay.
But if you apply the product unit, you get something bigger than 20, so that can't be right.
Yeah, you get your counting duplicates. Right, because if I choose to put my first digit here, second here, third here, I get the same numbers if I put my first digit here, second here.
Every time.
So you got to divide out the number of ways that you could have chosen to put those 3 digits. You get the same number.
somewhere, you can't put it in the same spot. So you only have 7.
All right, so let me talk really quickly about this, and then I want to tell you your homework for Wednesday, and then we're out of here. So, number of bit patterns that have exactly 3 ones. This is one of these questions that's a little easier to think about differently in terms of where should we place the first one. We've got 3 1 bits somewhere. So figure out where we want to place the first 1 bit. There's 8 places we can do that. And then figure out where to place the second 1 bit. That's 7 options. And figure out where to place the third. That's 6. And if we do that straight product rule, we're counting duplicates, right? We're saying that I'm going to put a 1 here, and here, and here. This is counting this as a separate number if we say I'm going to put a 1 here, and here, and here, when in fact it's the same number. So think about it in terms of combinations. Either do this and divide out the number of ways you can arrange these, or think of it as a combination. We're trying to choose 3 things out of 8, ignoring the order, right? So this is just 8 choose 3. And you can do some factorials and get yourself down to an answer there. So So that works for that. And then for bit patterns that have at least 2 1s, you can do that as a set of cases. So you can do this for 2 1s, 3 1s, 4 1s, 5 1s, 6 1s, 7 1s, and 8 1s, and then use a sum rule on those. So think about that. All right, so homework, supplemental questions from chapter 2. So I'd like you to look at questions 2, 4, 8, 10, 14, and 16. Write those up neatly and turn them in on Wednesday since we don't have school on Monday. And I will grade some set of those and get them back to you on Friday, hopefully.
The supplemental from what chapter?
Chapter 2. Say what? Yeah, I'll post it on Canvas, but it might be a few hours. So supplemental questions from chapter 2, numbers 2, 4, 8, 10, 14, and 16. All right, so have a good weekend. I will see you on Tuesday or Wednesday. Wait, say it again? So that only sets county equals to 0. All right, but it doesn't initialize on it.
Fight me all on it. She was like, no,